board. Okay, so the material, the discussion for today is one of the I think can be considered as one of the most famous meta heuristics other than genetic algorithms, which is called particle swarm optimizations. But particle swarm optimizations itself is, in terms of meta heuristic, is kind of new. It depends. If you I say it's kind of new means like it just developed in 1990s. Okay, so and I think that but since it's a very simple concept and it's relatively easy to be implemented, it getting the popularity and adopted in several optimization, adopted to be implemented in several optimization problems. And I will start with the contents here. Like you see, there is a lot of things because well, actually, if you go into deep about particle swarm optimization, there is a lot of things that you can configure. Okay, so what I want to deliver here, I want to give you some complete introduction, but since the time is limited, let's divide this into two parts. We just discussed the introduction part first. Hopefully we get into the numerical example, but if not, we can continue again on Sunday. Okay. So I also prepare a code for you and how to implement these algorithms. But again, coding for me, like I normally need like 2 hours to explain just the code itself. So that will take another 2-hour class. So let's see if we can spend some time on that one. But at least I prepare you the code. If you want to try it by yourself first, that's also good. Okay, and so since there is a coding for this one, so we have both course objective, whether it's formulating, it means like understood the mathematical foundation of these algorithms, and we will implement it using the programming language, because it's an algorithms. The easiest way to implement algorithms is using programming language. Okay, I will start from the philosophy behind the particle swarm optimization. As you can guess from the name, we have swarm. We have particle inside those swarm. It means like individual being in that is part of the community called swarm, or sometimes called flocks, or any population based in organism that work together, something like that. And we can say that these algorithms, okay, particle swarm optimizations is an algorithms that is inspired by how the intelligence of a swarm, of a group, of a community, in terms of their the way they behave in the nature. Okay. And particle swarm optimization itself is developed in 1995 by two researchers. One is electrical engineer, another one is a psychologist, if I'm not mistaken. So this is combination between people from social science with engineering. So they come up with the very beautiful idea, so-called particle swarm optimization. So basically, it mimics the social behavior or natural organisms such as bird flocking, fish schooling to find place with enough food. So if you see in the nature, when you see like fish schooling, there is a lot of fish swimming together and then finding we don't really see actually the pattern, right, from if we don't being part of them, but somehow we can see that there is some coordinating in between their movement. Okay, so how they move like that, that's actually the one that inspired these algorithms. So to make you have a little bit more clear how to say illustration about this, I think there is I found a video from this researcher, Craig Flox Reynolds. They create an animation on how those swarm or those swarm intelligence behave. They create those simulation. Okay, I think we can see this video, but since it's a YouTube video, let me stop pause the recording first so that we can upload this video rather easily later. Okay. So basically, there is 3 rules in that characterize those swarm movement. First is they tend to have separations in between those individuals, but somehow they also have the nature to have some alignment with each other and also have some cohesion to help this to steer the move of towards some position on as the behavior of their groups. Okay, and if we think about that, okay, in the PSO that proposed by Kennedy and Eberhard, so the one that we see in the simulation is not the PSO yet, okay, but somehow those characteristics, when you add one factor, okay, this one, it's called we can call it many names but here this one called Boyd earlier, right? And for that particular example, normally they call ruse, or if in our optimization problems, normally that is the objective function that we are going to find. Or for a flock, perhaps that is their attraction point or source of food, something like that. Okay, basically ruse or the attraction point is something that interests all of these individuals. So when we combine those 3 characteristics that we defined earlier with when they with the availability of point of interest for all of these individuals, so at the end of the iterations or the searching, all of these Boyds will try to find this ruse. Okay, so those are the concept that is being used in particle swarm optimization. So if we combine these 2 concepts with what we have in optimization problems, or in the context of optimization problems, ruse can be the objective function that we are going to find, and all of these Boyds, Boyds, right? All of these Boyds or all of these individual is the solution that actually represent the decision variables that is defined those objective function later. Okay, and the distance between ruse and the solution here, the individual here, that will represent how good is our last searching about the objective decision variables. Okay, now okay, so this is what I already talked about. And okay, in theory, so PSO or is representing a swarm of creature that could achieve things which normally not going to be found in the individual behavior. So it represents a swarm or a set of individual behavior where normally it has no self-control or no central control. It consists of cooperation and self-organizations, and it is simple yet powerful. Okay, so that's what make it interesting to be adapted as an algorithms. And it can be seen in many number of how to say behavior in nature, in several organisms that is work together in large number, like birds, fish, herds. It normally moves synchronously and changing direction, scattering, and regrouping. Those are the characteristics, the same with the voids that we already discussed. And for this particular particle swarm optimizations, it attracts many researchers because the simplicity of its implementation, and the code is rather simple, and there is not many parameters need to be adjusted in this algorithm. Okay, now we go to the more detailed concept. Okay, when you talk about optimization problems earlier, right, we have two types of algorithms: exact algorithms and approximation algorithms. We use approximation algorithm like meta heuristics like PSO because we want to get the solution fast, but we actually not really we already understood that the solution perhaps is not optimal. Okay. So to search the the possible solution for these optimization problems, normally called also as searching space, or the space that you are going to search to get those optimal solution or to get the best solution out of those searching space. And particle swarm optimization, each particle itself, its individual that you see earlier, that is move every iteration, is being used to search iteratively. So they will move from one position that is in the solution space to find the best solution in those particular problem. Okay. So particle represent the solution. Solution, what is solution? Solution is the decision variable that you are going to find, that you want to find in your optimization problems. Okay. And since particle representing the solutions, so particle should has attribute that represent those solution, right? Those attribute or those decision variable normally called position in PSO. Okay. For example, okay, find the optimum of this one, this curve. So find x. What is the mini? Sorry, not like this perhaps. Find the minimum x, okay, of fx. So find this one, okay, the minimum. So here, so what is this one? How this will be represented in PSO? So you will have a lot of particle here, for example, here, to represent this value, x equals something, x equals something, x equals something, right? This called position in particle swarm optimization. Okay, next. Now, when you have the position, okay, or the value, the solution that is the best among all of the possible all of the position that you already visit before, you call that one a best fitness. Okay. And it will be historically updated. So because every iteration you find another solution, another position, so you will each individual will note those position, the best position they ever visit, which is called the particle best or local best or p best. Okay. And okay, for example, if you have 10 10 particle. Sorry, 3 particle here. Particle this one, oh, the position here is X and Y, here is X and Y, here is X and Y. And then this one have, let's say we want to minimize, okay, minimize. This one have the objective equal 10. This one equal 5. This one equals 11, okay. Each individual will remember this position have this objective, this position have this objective, this position have this objective. So whenever they move to another position here, for example, X move to X and Y here, now the objective become 12. So they will still remember that, oh, my personal best is when I have the objective is 10 on this position. That is called the local best. Meanwhile, there is another term also for the best solution or best location denoted by the neighborhood. So in all of this, okay, among all of this, which one is the minimum? This one, right? So this will be selected as the global best or G best. Okay. And okay. So basically, PSO, every particle will try to continuously move or moving in or moving out on the searching space to find according to their local best and global best. So those are their the way they choose which the right direction will I go later after this iteration. Something like that. Okay. And okay, this behavior is commonly mimics the cultural adaptations of biological agent in a swarm. Okay, that's why we call this one PSO theory. So it's evaluate its own position based on the certain fitness criteria. So sometimes for one problem, this position will be evaluated like this. For another problem will be evaluated differently. Those way we evaluate, and then the value of that one will be based on the how do you define the fitness or how do you define those objectives. And then we will compare those with others individuals. So for example, this individual have position X and Y, the objective is something, and another individual have objective X and Y, position is something. So that will be compared, and we will find the best out of the all of the individual being searched the solutions. Okay, and okay, now for summary, based on that explanation, it means what? Each particle, okay, each individual in the swarm, we call it particle. That's why it's particle. Okay, each particle will move based on we can say the movement of one particle at each iteration will be influenced by several factors. First is its initial particle velocity. So normally the particle will be set with the initial particle velocity. It means they already have their direction at the beginning. Okay. And then, but that direction could be influenced by other factors as well. First is the social intelligence. Social intelligence means that whatever the best position among your neighborhood, that will somehow influence you, right? That happens also in real life. So if you see someone that, oh, he is doing good, what does he do for work? And then how does he manage his time, something like that. You always want to see and then want to try to do like him, right? Because you want to be as successful as him. So that one called social intelligence, to follow the global best, okay, the best position ever seen, something like that. And then another thing, you sometimes also have doubt, but if I follow that approach, I may success, I may not. But I am sure that I also already have my personal best, the best experience that I ever had. So that can also influence your movement, right? The same with the individual. Okay, so particle swarm move based on its cognitive or based on its personal experience. So we call that one personal best position. Combination between initial velocity, global velocity, and personal best will lead you to how you will go to the next iteration. Something like that. Okay. Particle location, velocity, personal best, and global best. Okay. Now let's talk about the flow. Okay. First, we need when you want to use particle swarm optimization, you need to initialize. Okay. Okay. So we need to initialize the particle first in the solution space, and then how do we initialize it? Okay, it depends on your problems. If you have an n-dimensional problem, for example, TSP problem, okay, for TSP problems, you have to visit the sequence of the city, right? Okay, the sequence of the city you can represent that in like this. For example, if you have 5 city, so you want to visit which city first? 1, 2, 3, 4, 5, 6, or 2, 3, 1, 5, 6, 4, something like that. Okay, it means that you have 1, 2, 3, 4, 5, 6, 6-dimensional problems. Okay, and then how do you use PSO for this one? You need to initialize random number here. Okay, 0.1, 0.2, 0.3, something like that, 0 point something or 1.5, something like that. This is how do you initialize the particle in the particle swarm optimization. Okay, later after you initialize it randomly, you need to evaluate the fitness based on the objective value. Okay, so after you initialize those number randomly, you need to convert it to the route. For example, the one that I showed you earlier, 0.1, 0.2, 0.3, 0.4, something like that. This is 1, 2, 3, 4. So you sort this number based on this value, and then you will get, because it's already sort, so 1, 2, 3, 4. So this one will be evaluated as the solution. You will calculate how is the objective value for this particular route for the TSP, for example. Okay, and then so later you want to check if the fitness or the objective function, if TSP will be calculated based on the total travel distance, for example, if the fitness or the objective value of one particular particle is better compared to the previous locations that it already visit, it will consider as the new personal best. But if not, we can always use the old personal best. But since if it is the first time you create this individual, so the personal best will be equal to the same value with the first objective function that you already has. And the same way with the fitness for the global base or the entire population base. So you need to check among all these iteration, among all this population, individual in this population, which one is the best? Then that one you should consider as the global base. And then after that, you will update the velocity, or you will create a way to move from this particular position, particular location to another location. Okay. And the question is now, how do you move from one particular location to another location? PSO will use this formula to determine how do you use from one particular location to another location. First, you need to update the velocity. Velocity is the value of that you calculate based on these 3 factors, 1, 2, and 3. The first vector is the individual velocity or initial velocity, right? The one that you see earlier in that picture that we saw, this one, W multiplied by VI. That is inertia, their own push to move somewhere. And the second one, R1, C1, what is R1, what is C1, later we will explain. But basically this one will be based on the, you see, P base is personal base. So it's their cognitive intelligence. So this one will represent a factor, how you will deviate from the current approach to based on your cognitive, previous cognitive experience. And the last part is the social intelligence. It means that based on the global base, you will move toward that global base at some variation, something like that. So this formula is basically represent that movement in the PSO. Okay, so W is we call inertia wave, or the initial, to determine the initial how they will deviate from the initial solution, initial velocity. And then we have R1 and R2 is a random. You can see in the formula there is R1 and R2 here. Random 1, random 2. It's a random number uniformly distributed from 0 to 1. It's just to add the stochasticity to make each swarm mimics the behavior of the swarm in the real life. Okay. Okay. And then we have C1 and C2. C1 and C2 is a constant. It's a parameter that we set to determine how large is the acceleration. Acceleration means the push toward the personal base or toward the global base. Okay. Yeah. So after you calculate this V1, you will need to update the location now. So after you have this one, okay, P, you update this one. So the next location, xt plus 1, is equal the current location plus the next velocity. So let's say the initial wave is going toward here, but you know that there is how to say, influence to go to personal base, or there is influence to go to global base. So finally, combine these three factors, you have another factor here, something like that. Okay. Yeah. Okay. So now we continue to talk about the basic flow. After mentioning those several concepts, now you can see that a PSO model is learning from their own experience or behavior of individual particles that reflects the social interaction phenomena among those particles. Okay, there are two terms here. You can see that stochastically weighted. So random 1 multiplied by C1, random 2 multiplied by C2. This one, R1, C1 is represent how they will deviate from the own experience. Okay. And R2, C2 to reflect on how they will deviate from the social interaction. Okay. This randomness provides the possibility to reach global optimal. It means that if we don't use random, what will happen to the PSO? If we don't use random number, PSO will always move toward one particular direction, right? But meanwhile, if we use random, this one will let the individual to search more space, to balance between exploration and exploitation, like we explained in the meta heuristic session last week. Okay. And this one is the pseudocode. Okay. The pseudocode is like this. So basically, we normally denote the solution with X. Okay. X is the solution. Xi means how many decision variable will be in the X. For example, if you have two decision variables, so you will have X1 and then X2. If you have three, then X3, something like that. And then like for example, TSP, they have the number of X will be represented based on the number of the city. And then okay. So first we will initialize the swarm or xi randomly. It depends on how many swarm individual we want in each swarm. For example, if you want to have sorry, AI is yeah. Okay. So if you want to have the 10 particles, so you have like a number of particles until 10. So, and then you will evaluate each individual, okay, each particle. Okay. And then after you evaluate each particle, for all particle, there is several steps that you need to do. First, you need to update the velocity. Okay. It means that where do you want to move this particle next based on the formula that we discussed earlier. There is inertia wake, there is personal best, there is global best. Okay. And then after you get the new position, you need to move to that new position, which is the position X. Okay, multiplied by equals to current position plus the velocity that you calculate earlier. Then you need to update whether the new position is better than the personal best that you already have, or if the new position is better than the global best that all the organism, all the individual is already have. And then you update those velocity, and then you see if it is exceed the constraint or exceed the position or exceed the velocity limit, something like that. There is an explanation for that later. And then okay, yeah. Now this piece pseudocode, it is better if we can explain in the numerical example, so that is more clear. But before that, let me ask you, maybe you will not have any a little bit, just a little bit. Maybe you will have just a little bit. How to say? You don't get it yet. How does this one work? But after this numerical example, perhaps it will be better. Okay. Let me show you one example on how PSO can be used to solve one simple optimization problem. For example, here we want to find the solution for this optimization problem. Very simple. You are asked to find the maximum of this function. Okay, x multiply the power of 0.5, so it's a square x minus 1 divided by y. What is the optimal value for this one? Okay, well, actually we can use calculus, we can use anything, but this is just for example. So how particle swarm optimization can be used to solve this type of optimization problems? And we know that the value of x and y should not be it's limited from 0 until 5. Okay, Okay, we will use this algorithm and illustrate the PSO algorithm. So first, okay, the first step in PSO algorithm, as you can see here, random initialize solution. Okay, so here you go, we will random. Okay, now you can see that what is solution in PSO. One solution is this one, like this one, you have 1, 2, 3 individual in the swarm. So you can see in the picture here, first individual, second individual, the third individual. Each individual has their own location. Okay, here, individual 1, okay, individual 1 have x equal 1, y equal 2, x equal 1, y equal 2. Individual 2 have x equal 4.5 and y equal 4. Okay, so this represent each of these represent one individual in the swarm in the PSO. So their location will be what? Will be the decision variable. As you can see earlier, what is the decision variable of this problem? X and Y. How many the location of X or the value of X and Y will determine what is the max of X, Y equals X to the power of 0.5 minus 1 divided by Y, right? This will determine this one, the value of X and Y. So for PSO, first we need to initialize the random number for this one. And then we also need to have the initial velocity, okay, because we will need this one later when we calculate based on the formula that is discussed earlier. So you can read this one rather randomly, okay. But for this one, generated randomly, the location, but it should not be less than 0 and it should not be greater than 5, right? This is one rule that already said earlier. Okay, next. After you random the initial solution, then you need to evaluate. Evaluate means calculate the fitness value. Okay.
Dr. Vera, can
Yes.
I ask?
Yes.
For
Please.
the before this slide.
Yes.
So what if you have real data? Would that be the one in the location, for example?
Okay. 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 Now the location will represent what? The decision variable, right? The decision variable, it really depends. This one, the decision variable is X and Y, right? But for your optimization problem, for example, it can be binary, right? X from 1, 2, 3, 4 can be 0 or 1, right? Or it can be a real number, or can be several type of decision variable. We will discuss that later. But the value of this X and Y, it not always be X and Y. It can be like X1, X2, X3, X4, X5, something like that. It really depends on your decision variables. Okay. So may I ask what kind of problem you are working on?
Nothing yet, because I'm
Okay, okay.
imagining what I can do with
Okay,
particle
okay.
swarm.
So basically, this can be modified into the decision variables that you will use, that you want to optimize. Okay. For this case, there is two decision variables. You want to find X and find Y. Okay. Later on, if you want to use, for example, for PSO or for DSP, this will be different way. This will be not X and Y only, something like that. Okay, we will discuss about that again later in the other slide at the end of this presentation.
And then for the velocity, would there be any range for the estimated value?
Okay, for this one, actually, velocity, it's really depends. Really depends on the value of your decision variable. For example, if you have the decision variable is limited from 0 to 1, it is wise to estimate the velocity should not be greater than this one, right? For example, your decision variable, I know that my decision variable should only be from 0 until 1, can be 0 0.2, 0 0.3, 0 0.5, something like that. So to velocity will be combined with this location later, right? You will x plus v, right? The location will be plus the velocity. So the initial velocity, it is better to according with the value, the range value of your location. Okay. For example, if you have another example, this one, the location is from 0 until 5. So that's why they generate this one from range -1 until 1. But for your, if you have another problem, my problem actually determine the optimal inventory, for example. Okay, of inventory can be from 0 until 100. There is a range for that one, for example. So the velocity, it is better to be large also as well, like this. This can be limited from 1 minus 100 until 100 plus 100, for example. So this another way. This is also need another setting as well. Okay.
Okay, thank you so much.
Okay, next, you need to evaluate. Okay. So when you have this location represent what? Location represent the uh, uh, decision variables. So decision variable is here x and y. So you need to plug this one x and y. For example, x is equal 1 square root of 1 minus 1 divided by 2. So you will get this one, 0.5. So this is the objective value or the fitness value for the first individual is 0.5. Okay. The first individual is 0.5. The second individual is 1.871. The third individual is minus 0.268. Okay. So now, based on this evaluation, you want to find the maximum one. Okay. So you will need to next, you need to determine which one will be the G best or global best, which one will be the global best location. Okay. So here, the global best, you want to find the maximum one, right? Even if it is a minimization problem, the global best will be the last one. But this one is maximization problems. So the one that has the maximum fitness function is the second individual, and we will use their position, their location as the global best location, and their fitness value as the global best value. So this one represented by these dots here. Okay. Okay, and then next. For the first iteration, we will use the same location and then the same fitness value for each particle as their personal best, because they don't go anywhere yet. So that will be their personal best. Okay. So now we have the best global best and global best location. Our next step is what? Next step is to calculate the new velocity. Okay. Because every iteration we want to move. Okay. Along this one, we don't know, right? Which location actually is give you the maximum of this function. So at each iteration, we will try to move the particle to explore. Sorry, where is it? At each iteration, we will ask the particle to explore this searching space. Okay, this searching space, and then they will give you result. When they go here, okay, this is my new location, or go here, this is my new location, this go here. They will give you the update. Oh, this one is the best location, or here is the best location to for this particular problem. So that's how actually the particle swarm optimization works. Okay. The question maybe for you for now, like my problem is not only two-dimensional, not only X and Y, can be like X, Y, Z, can be X1, X2, X3, X4 until so many X I need to find. How should I define that? How can I use PSO for that one? It's basically use the same concept. You just need to extend the number of the decision variable here. Okay. Later we will discuss about that. Okay, and then okay, now we use simple example first. Two decision variables. Now you need to update the velocity. How do you update the velocity? Using the formula that is already discussed earlier. This formula V initial velocity, initial weight. This one is the personal best. This one is the global best. Okay. So for example, the new velocity for the first individual is this one, 3.4 and then 1.0. How do we get with this one? Okay, first we go to okay, the initialization here, right? Here is the initial velocity 0.85 minus 0.51 for the individual one. You can see here for this particular decision variable or location X, one is the parameter for the inertial weight, and then 0.83 is their initial velocity. Okay, this one W multiplied by VI minus 0.51. Okay, and then plus, okay, plus C1. This one a random number, but I didn't see why they don't put it here. But somehow just like you put some random number here and then one parameter here, C2, here is 2. And then because the personal best, the value of personal best and the current location, it should be the same for the first iteration. So this one will be 0. Okay. And then R2 and C2, okay, here they mention the random number 0.38, and then here is 2. Okay. Oh, sorry, because this one 0 and 0, so it doesn't matter this value, so no effect for this one. And this one here 0.38 is the random number that is appear. It's from 0 to 1, and C2 is the parameter. It's equal to 2. And 4.5 is actually the, here you go, global best for X, right? Yeah, 4.5, and then 4 is global bias for Y. Yeah, 4.5 and 4 minus, okay, 1 and 2. So it means that the differences between this one, their particle location with the global base, will be considered as the vector to move on the next velocity, something like that. Okay. So here, let me repeat again. This one is initial velocity for X in the individual one. This one initial velocity for Y in the individual one. You multiply by 1 because this is the parameter that they use. Okay. And then plus this one doesn't matter because it's 0. Okay. So you don't need to calculate this. And then this one, this is a random number. Okay. This is a parameter R2 and C2. And this one, 4.5 and 4 is the global base of the current iteration. Iteration 1, we have the last particle as the global base, right? Sorry, the particle that is located 4.5 and 4 as the global base. And it is minus by or reduced by this particular location of the particle. This particle current location, okay, 1 and 2. So then this value, you will get a new value here, 3.5 and 1.0. Okay. You can try to calculate it, but I normally not doing it, but I'm sure that this pretty much the number is already okay. And then for the global base, you also need to calculate velocity, even though they are in the global base right now. Okay, so but the one that is affected is only the initial velocity here, previous velocity. 1 multiplied by minus 0.67 multiplied by 0.94. So it is still in the current velocity. Something like that. Then the last one you need to calculate is the last individual. Last individual, they also have the current velocity, and then current velocity, and then this one doesn't matter because it's still the same, and the differences between the global base and the current location of this particular individual. So you will have the new velocity here. Okay, new velocity here, and then you will update the new location. Yeah, okay, the new location, sorry, the old location plus this velocity plus this new velocity, and then you get new location. Okay, let me give you the example here. Okay, here, this is the old location. Okay, the first initial location that we already evaluate, and we get this one as the global base. Okay, and based on this global base, we calculate new velocity. New velocity. Here. Yeah, new velocity. The old location plus new velocity is the new location. Yeah. Okay, and this one we will do the same process again. Evaluate new, check it whether it's better than the previous one. But before that, we need to do another evaluation and update the personal base and global base also. Okay, so basically, if we illustrate this movement, all of the particle is moved. All of these two particles will move toward the global base. You see here, they move here because it is designed that way so that if you have the better solution, your algorithm will try to go there to further explore that area, something like that. Okay, that is the first iteration only in particle swap optimization. I think it's already make you a little bit confused, right? But that's okay. Later on, you will catch up after you see again more example, and then more, especially when you already able to code it. Normally, it's already you will fully understand it that way. So that's why actually exercise is really important in implementing meta-heuristic algorithms. Okay, after that, what we will do? We will do another iteration. Calculate the objective value first. Okay, and then this is the new location, right? We calculate again. Put all of this value to here, and you get new fitness. Find the best solution, which is here, global best. And then here, you do the same thing again. So here you go. Okay, and then but here you need to also update the personal base. Okay, previously we don't have to update the personal base because it is the first iteration. We don't know which one is the personal base. Okay, so now here you need to update the personal base. You can see location here this is the new one. You compare this one. Okay, here is 0.5, this one 1.75. Okay, so the location in the next one will be their personal base for the particular one, individual one. But the second one, you see, 4.5 and 4 is 1.87. The new location, as you can see, is 1755. So the old one is much better than the new location. So the personal best is taken from the previous one. So this will be their personal best. Okay, but for the third one, it is clear this one is minus, this one is 1.999. So this will be their new personal best. That one is updating personal best. Okay. Next, after you do update the personal best, you do the same step with the previous iteration. See which one is the global best. Okay, now I get this one is the global best, the third location. Previously is the second location. But now the third location become the global best. Then what you do next? Okay, after you find the global best, calculate again the velocity, update the velocity again. But we keep that one for later. We will see it the numerical for that one. But basically, all those iteration is repeated in the PSO concept. So at the end of the iteration here, so after several iteration, after the stropping criteria, you will expect that the global base that is found as in the PSO is the best solution that you can find using particle swarm optimization, because as you can see that they always find, okay, after this one, this is the second iteration, you go another way here, go here, and then go another way here, something like that. Try to explore all the possibility here, but in a more guided way, so you can expect that at the end of the iteration, the global best will represent the best solution that they can find. Okay, there is several things can be considered here. First is how do you constrain the velocity and location? For example, previously there is a consideration if you move too far, the searching will be not efficient. So there is a mechanism to limit the velocity during the searching process, in which you can use this formula, or it's several. Basically, there is several things to do. For example, whenever it's go more than several facility, okay, you will use that particular maximum velocity, something like that, or using this formula to represent the velocity. Okay, velocity, we called it velocity dumping, is also sometimes important because when you have a wide searching space, you sometimes you want to move fast at the beginning to explore more area, but at the end of the iteration you want to move a little bit slower in more limited spaces. Okay. And then another things for boundary. Okay, for boundary, it's like this. Previous example we have, it is the x should be from 0 until 5, right? And the y also from 0 until 5 here. So we can see that sometimes the particle will be moved outside this boundary. Okay, it's like constraint if in our optimization problems. So if it is moved from out from the boundary, what should you do? There is several ways. Okay, you can let the particle stick at the boundary. For example, oh, if you move here, you keep it here until there is some moment make you go out the other way. Or you can use the bounce back mechanism. For example, if you go here, then you can bounce to this one. Or you can move the re-entry. For example, you go from here, then you re-entry from here. That's also possible. There is a lot of way to do that. Let's see one example on how we can continue this numerical example. and then see if it can represent the velocity dumping or boundary checking later. Okay, first recap. We are in the second iteration, and we have this velocity, we have this location, okay, and this is the p base, and then this is the global base that we have. Okay, and then okay, now we continue to the next iteration where we need to calculate new velocity. Okay, calculate the new velocity using this approach. How do you calculate this? Yeah, the same way. The 1 multiplied by the previous velocity plus random number multiplied by 2 multiplied by this one is the difference between the personal best with the current location. Okay, the last one is the R1 random 1 multiplied by random 2 or C2 multiplied by the difference between the global base with the location, your current location. Okay, do that one for each particular individual here, individual 1, 2, and 3. Then you will get the new velocity here. Okay. I know it's not easy to calculate manually, but this normally will be implemented in the algorithm. So you will do this one automatically using code. Okay. And then you can see that when you add the velocity to the new the location, this is old location, right? This is new velocity. Here we have the velocity dumping. You can see that here. Whenever it is more than 2, you want to limit the velocity into 2. Okay, so you can see here. Velocity dumping, it is limited when it's more than 2. How do you determine 2? It is a parameter. Okay, it is the things that you need to select. Then after that, you plus the old location with the new location. Okay, and then you get the new location here, and you can see that many of them is more than the boundary that we have. So we need to use one mechanism. For example, here the example they use, if it is more than the boundary, then you stick it to the boundary, become 5 like this. That is one mechanism, but there is another mechanism that we can see later. Okay, so basically it's moved like this. Okay, this is the last iteration that I show you the illustration in the figure. Okay, so it moved from the first iteration, it's square here, from here to here, yeah, all move to this one, yeah, like this, and then from this one they move like this. So there is 3 steps that we already shown. But basically here what I can illustrate from those type of problems, normally they will move a little bit far and then try to find the pattern first, and then after they see there is a lot of good solution in nearby here, all those particles will be going into the same direction here. At the end of the day, they will how do you say, clustered nearby the best solution here. Okay. Yeah, that is the illustration of particle swarm optimization. Now I already explained a little bit in the basic concept. This one will be explained tomorrow, including hopefully we can code the particle swarm optimization. Okay, up until this one, I hope you still get the point. But for master degree student, I think it's okay because you will not need to implement this one. So let's worry about that. But for master degree, for PhD, perhaps later you need to learn about it and then try to implement it. Okay.